All right. Hello, everyone. My name is Emma Jaggi, if you're watching this, and I was asked by Dr. Mortensen to give a presentation on Lecture 6, and that is talking about the emission spectrum and Bohr's model of the atom. So let's get right to it. I'm going to share my screen. All right. Let's go to the beginning. And I'm going to present this to you guys so you don't have to look at it like this. Slideshow, play from start. Beautiful. Okay, like I said, I will be talking about the atomic spectra and the Bohr model. So, what is a continuous spectrum? Well, a continuous spectrum comes from, it's visible to us, and it is energy that comes from dense gases or solids that radiate heat. They emit radiation over a broad range of wavelengths, like it says, and so it looks continuous. And spectrums appear in colors, so they appear and show up in colors. And you can see in the photo, it's red, orange, yellow, green, blue, and violet, because those are the visible light colors. Next. So these black lines, what are these black lines? Do you know? Take a guess. These are called Fraunhofer lines. He is just the scientist who researched them, and yeah, he knew a lot about them. And like I said, because of these, we have been able to determine what the sun's atmosphere is made of, and other things, but I just thought this was a cool fact. How comparing sun's solar spectrum with the absorption spectrum of certain substances. So I don't know if I mentioned this, but these black lines are absorption. So you can see that there are Fraunhofer lines here, EDC, and there are more, but yeah, so everywhere that it's colored, it's radiating light, and everywhere that it's black, it's absorbing light. So thank you to Joseph von Fraunhofer. Something interesting about spectrums is that every element emits a unique and specific wavelength. So no single element is the same as another. They're all different because they're all composed of different substances. And hydrogen actually has one of the most unique emission spectrums. And that is because it is most, I'm trying to remember the fact because I didn't write it on here, but I believe it's one of the most stable, and that's why it's unique. But as you can see, hydrogen, this is its emission spectrum. Helium, it emits a bit more than hydrogen. Neons, sodium has a smaller one, it emits less light. Then we've got mercury. And this right here shows a display of the intensity and the wavelength. Okay, emission versus absorption spectrums. So if you're trying to determine what an emission spectrum looks like, what an absorption spectrum looks like, here up at the top, it's continuous. So it just continues. There's no emission or absorption like particularly shown here. It just continues. And an emission spectrum has mostly black, and these lines are where it's emitting light. So all right here, this red, this yellow, this green, it's emitting light. And in an absorption spectrum, you'll see these lines are where it's absorbing. So it's pretty easy to tell the difference between the two. These black lines are absorbing, the rest of it's what's being emitted. And then the same with the emission spectrum right here. This black is absorption, and its emission is these colorful lines here. Okay, the Balmer series and Rydberg equation. Sorry, I don't know if you guys can see this. I have to keep moving my face so I can read the slides. See if we can just leave it at the top right. There we go. Oh, okay, so Balmer series and the Rydberg equations. The Balmer series are visible lines in the hydrogen atomic spectrum. And Johann Balmer, he was the one who discovered a mathematical formula relating wavelength to n, which is an integer. Sorry, okay, good, I'm off mute. I was worried I was on mute for a second and I was like, oh no, I've been going this whole time. Okay, let's go back to the PowerPoint. Yes, so like I said, he was the one who found the visible spectrums in the hydrogen spectrum. And he didn't find them, but he used those to find a formula relating the wavelength to n. And Johannes Rydberg was the one who generalized the equation to predict the spectrum. So the Rydberg equation is displayed here in this orange box. That right there is a sign for wavelength. The r is a constant, and then the n is the integers with regarding energy levels. So N1 is an energy level, N2 is some energy level. And it's got to be a larger energy level subtracted by a smaller one. So you can only use this equation for things that are absorbing. Yes. I'm trying to remember that. We talked about it in class today, but you can only use this equation in specific circumstances. So watch out for that. Okay, Bohr's model of the hydrogen atom. So there are a couple things that are important to remember about Bohr's model. And the first is that electrons only occupy certain stable orbits. And allowed orbits have quantized angular momentum and energy. N, which you'll see in equations, is the principal quantum number, and it designates the energy level. And lower n values are closer to the nucleus. So if you can, I don't have a visual, but this would be a smaller n value, like n equals 1, n equals 2, n equals 3, n equals 4. So these lower n values are closer to the nucleus and lower in energy, where the larger are larger in energy. And I actually have, oh, let's go back. I have a video that I would like to show you guys. If I can exit out of this, I'll go back to screen sharing, don't worry. But this gives a really good display of Bohr's model of the hydrogen atom, and it really helped me to understand it. So we're going to watch that together. Copy. Make this smaller, and we're going to YouTube. Edit, paste. Hang in there, we're almost there. All right.
I didn't realize how many mistakes I was making in English until I started to use Grammarly.
It's like having a proofreader.
Skip the ad. Here we go.
Professor Dave here. Let's talk about the Bohr model of the atom.
He knows a lot about the science stuff. Professor Dave explains.
Once Einstein extended.
Sorry, guys. I'm trying to get to my desktop. There we go. Okay. I thought it was sharing, but I don't think it was. Where did it go? Okay, here we go.
Planck's idea of energy quantization to electromagnetic radiation, other physicists made some similar strides. Niels Bohr was dealing with some problems that were arising with the structure of the atom. If an atom has positively charged protons and negatively charged electrons, why are atoms stable? Why don't the electrons just collide with the nucleus? And what were these emission spectra that we can see? What is it about different elements that makes them emit light of different colors? Bohr answered these questions with his model of the hydrogen atom. He extended the idea of energy quantization and said that the potential energy of the electron in a hydrogen atom is also quantized. This means that an electron can't have any imaginable energy, but can only inhabit certain energy levels that are at fixed distances from the nucleus. Each type of atom has its energy levels at different values due to its unique number of protons in the nucleus. And an electron will transition from one energy level to another when a photon of a very specific energy is either absorbed or emitted by the electron. The energy of the photon will correspond to the difference between the two energy levels. So if the electron in a hydrogen atom goes from the n equals 3 to the n equals 2 energy level, a photon will be emitted that is equivalent to that specific energy gap. Another transition has a different energy gap associated with it, and therefore generates a photon of that particular energy. And to go from lower to higher energy levels, an electron must absorb a photon of that particular energy. For a hydrogen atom, the energy levels depend on the Rydberg constant and are given by the following equation. But we typically just measure the change in energy of an electron during a transition, so we can modify this equation to include the change in the energy level. N final is where the electron ends, and N initial is where it begins. Using this equation, we can predict the wavelength of photon associated with any possible transition for the hydrogen atom. Take this transition, for example, from 4 to 2. Plug in where the electron starts and where it ends, and we get the change in energy of the electron, which equals the energy of the photon. From energy, we can get frequency, and from frequency, we can get wavelength.
All right, and I just want to pause and focus on that because these are problems that we went over in class. So as he showed, you can use that equation right there to see when you're going to find the energy difference, when you're going from one energy level to another. So in this example, it was going from an energy level of 4 to 2. So the initial 4 went here, the initial 2 went here. Rydberg's constant is always the same. And so he multiplied those out right here. There's Rydberg's constant, and he got negative 4.09 times 10 to the negative 19th joules. And then he continued.
From energy, we can get
So this is the energy of the photon that we just solved for.
frequency.
And now he's solving for frequency because we want to finally end up at wavelength, but we've got to do a little bit of rearranging with our equations.
And from frequency, we can get wavelength.
All right. So right here, he was substituting for V, since C equals the wavelength times V, velocity. And then he has E equals hc divided by wavelength. And then you solve for the wavelength. I can't remember the exact names of H and C, but C is a constant. So, and then this is his equation as he's solving for wavelength, and he gets the wavelength of 4 times 10 to the negative 7th meters.
We group the transitions according to the energy level they land on. All the ones that end on n equals 1 are called the Lyman series. The ones that end at n equals 2 are the Balmer series, and so forth. Notice that the energy level gaps decrease as n increases, and n equals infinity is actually a finite distance from the nucleus. If an electron goes beyond that, it is considered to have been ejected from the atom. The Balmer series happens to contain transitions that generate photons of visible light. These are the ones found on hydrogen's emission spectrum. These lines correspond to the electron's transitions that end at n equals 2, and the resulting photon that transition emits, which just happens to fall in the visible spectrum. As we said, these energies are unique to hydrogen. Every element will have its own emission spectrum because every element has a unique nucleus and therefore differently spaced energy levels. In this way, an element's emission spectrum is sort of like a fingerprint unique to that element. This is how we can know the composition of objects in space, by analyzing the light we see. Let's check comprehension.
All right, you guys can pause if you need more time, but it's what is the wavelength of a photon emitted when an electron goes from n equals 6 energy level to n equals 3 in a hydrogen atom. So we're going to use that equation that we have with the, yes, there it is. I can't remember the name of it, but this where we've got the initial and the final. So we're going to start with that and Rydberg's constant. Then we get that, and then we're going to use this snazzy equation, which we substituted values in for, by the way, to solve for the wavelength. And you're going to have to rearrange this equation to solve for the wavelength, by the way. So it'll end up, you'll multiply that wavelength over, divide by E right here, and it'll be hc divided by E, which is the change in energy. And you'll get this wavelength of 1.094 times 10 to the negative 6 meters. And if you don't understand how this works, I would recommend pausing this and gaining that understanding for yourself. Oh, and now we're waiting, as I just explained.
Thanks for watching, guys. Subscribe to my channel for more.
Thanks for watching. It was great. Thank you, Professor Dave. He explains much better than I do. So I hope your understanding is a little bit better after that. Let's see. Let's go back to screen sharing. All right, here we are. So that was Bohr's model of the atom. Absorption and emission. So we kind of talked a little bit about this when an electron is going from a lower energy state to a higher energy state. So for example, n equals 2 to n equals 4, it's absorbing. When it's going from a higher energy state to a lower energy state, like n equals 5 to n equals 1, it's emitting. And you can see that displayed right here. It's absorbing, going to a higher energy state, emitting lower energy state. Even ground state can go to as well. Excited states are the higher energy levels. So an electron is excited when it's in a higher energy level. Let's see what I have. Yes, and this is just kind of explaining how they do that. Electrons relax to lower energy levels by emitting a photon. And electrons can't exist between energy levels. They're, like Professor Dave said, they're quantized, so they have to be in a certain specific energy level. They can't be in between ever. So how do we see colors? This is kind of fun. Well, the colors we see are reflected colors. So the colors we see are not the colors that the object is absorbing. So when we look at a green tree, it's not that the tree is absorbing green light, it's that it's actually absorbing all of the other colors on the spectrum except for green. And because of that, we see a green tree or a pink pencil or the blue ocean. So that's unique. And here is another practice problem. These are important. So practice, a red laser pointer emits light with a wavelength of 700 nanometers. A fancy green laser pointer emits light with a wavelength of 500 nanometers, which emits more energy per photon. So we're looking for energy. That's what it's asking us for. And that's what I said right here. We're looking for the E value for both. And we are going to have to rearrange these two equations right here, as Professor Dave did, and as we'll probably have to do on exams. So you get E equals h times wavelength over velocity. Wavelength over c. That it's supposed to be wavelength over c, sorry. That is an error. But yeah, you do that by rearranging this. You solve for v, the velocity, and that is c divided by wavelength. And so that's what we do here. The green laser emits more energy per photon, and here's the work. I won't stay on this for very long, but I would recommend pausing it so you can understand. Here is this equation right here, the hc over wavelength, and then you plug those values in. And h is a constant, by the way, so is c. And then the wavelengths are different. So just watch out for that. You've got the same on the top, but you've got those different wavelengths of the green and the red on the bottom right here. So it's emitting 4.0 times 10 to the negative 19 joules for green, and it's emitting 0.028 times 10 to the negative 17th joules for red. And because of that, we can see that green emits more energy per photon. And you want to be careful actually with these values when it's in this form, because it could be that actually the red emits more light. I mean, we know the answer, but be careful with 10 to the negative 17th, 10 to the 19th, exactly where that decimal ends up, because you don't want to get that wrong on the test. So just look out for that. The energy of the green is also greater than the energy of the red, which is, yeah, that's why it emits more light. More energy per photon, excuse me. And that is all. Thanks for listening. I hope you guys have a better understanding now of Bohr's atomic model and emission spectrums, and that you continue using those practice problems. Also, I recommend Professor Dave Explains for a lot of topics because he explains really well. And good luck on the exams. You guys have got it. Thanks so much.